Hello and welcome to episode 7 of this lecture series on smell. And today's perfume is not a perfume at all. It's in fact a B vitamin complex sold as a supplement. And it smells like thiamine, which is vitamin B1. And I will explain later why this is relevant to today's lecture. So in the last lecture I explained that while reading this textbook of chemistry in a hotel in Lisbon, I determined to my own satisfaction that BH bonds should vibrate roughly at the same frequency as SH bonds, and therefore, if the vibrational theory was correct, they should smell of sulfur, and nothing else in nature does. So I started looking into the possibility of obtaining some of these famous BH compounds called boranes. And the good news was that there were plenty of boranes around, but the bad news is that most of them, in fact almost all of them, were either spontaneously explosive in air or rapid decomposition due to water vapor or otherwise unstable even in a vacuum. All of them were toxic. Basically just a disaster. Very hard to get hold of, and when you do get hold of them, you can't open the can because it'll explode in your face and set fire to the lab and all this stuff. Now, boranes are really interesting compounds. They're very strange. And in fact, their chemistry, their instability and so on means that they're used, for strange purposes like rocket fuels. Their structures are strange. I can't resist mentioning the structure of diborane, which was first worked out by a man I hugely admire called Christopher Longred Higgins. He determined from first principles the structure of diborane while as a second year undergraduate at college. He proposed it in his second year at college. And here is the structure, and you can see that anybody who is used to normal, everyday organic chemistry looks at this molecule and thinks, what is going on? Because it has bridging hydrogens. Normally hydrogens hang off at the end of a carbon or a sulfur or an oxygen. In this case, two of the hydrogens of diborane, which is B2H6, actually bridge the boron atom. This is deeply weird. So anyway, I couldn't find any boranes, so I figured I might as well just call up the companies that make them and see if they can supply me with a sample. So I found a company that made boranes, and I called them up. And of course, they made boranes for a reason. They made boranes as rocket fuels. So when I spoke to the chief chemist at the company, I said I would love to have a sample of, I believe it was pentaborane. And the man says, sure. And I said, okay, well, what's the smallest sample that you can send me? And he says 10 tons, which of course, if you're making rocket fuels, 10 tons probably goes through in a few seconds. But for me, that was an awful lot of borane. So I said, no, I don't think I can deal with either buying it or handling it or anything. So I said, okay, let me ask you a question. What do boranes smell of? And he said, sir, I try not to smell them. Okay, so that was the end of the conversation. And I looked in the literature, and it was pretty much a recurring theme that they smelt bad. Even the earliest descriptions of boranes, they burn with a bright green flame. They're very peculiar in that respect. The color of the flame is strange. People had noticed what they described as unpleasant, a foul odor. And so I found this very encouraging because people hate the smell of SH generally. And so if the boranes had been described as having a pleasant ethereal or floral odor, that would have been the end of it right from the beginning. So looking through the literature, eventually I found a borane that did not blow up in your face, that did not decompose in air or water vapor or any such thing. In fact, pretty much stable, very pure because they're purified by sublimation, which is going directly from crystal to crystal where the impurities are eliminated. And it was called decaborane. So I went to the library And I looked up decaborane, I found the reference, and I looked up decaborane, and everything looked pretty good. I mean, it had the right vibrational frequencies, it had lots of hydrogens vibrating at the sulfur kind of frequency, so I thought, this is great. And then at the end of this paper, I looked at the text, and it said, to my surprise, it actually described the odor. And it said, a pungent chocolate odor. So I thought, what? Pungent chocolate odor. First of all, chocolate is not pungent. Pungent is something that makes you go, recoil, like fishy smells or something like that, or ammonia. So pungent chocolate odor. Chocolate is a pleasant smell. It's also a very complex smell. And very specific. I was very surprised that they would describe it, but I didn't think that was great news because I was hoping they would say repulsive sulfur odor. Anyway, looking around in the various chemical catalogs, to my great surprise, it turned out that you could buy decaborane very easily. In fact, the main supplier that we used in those days, called Sigma, would send it to you overnight. 1 gram of decaborane in a little bottle. So I ordered it. And after a couple of days, it was delivered to the department, so I went and picked it up, and there it was. And this was basically, at that point, it was a sort of a do or die thing. Either the decaborane would smell of sulfur, in which case there was no way that this could be a coincidence. Same vibration, totally different chemistry, unique vibration, smell of sulfur. Or it smells of something else. And the idea of a vibrational theory was simply wrong and therefore should be abandoned immediately and permanently. So I brought it up to my lab, and I was so nervous that I thought it would help my nerves if someone else could also smell it with me, so that we could compare our sensations. So I went next door and I asked a colleague to come, and he knew what I was up to. He knew the point of the whole experiment. So I handed him the little bottle, and before I could do anything, he opened it and he smelled it and he went, boiled onions. And I smelled it and I thought, yeah, boiled onions or leeks or something, but basically a sulfur smell, because onions and leeks are full of sulfur compounds that are extremely powerful and very distinctive. So it was a sulfur smell, and we were just so stunned. It took us a minute or two to even recover from this, and we started jumping around and shrieking with surprise and joy. So decaborane smelt of sulfur. If you want to find out for yourselves what decaborane smells like without actually smelling decaborane, which is toxic and rather dangerous, you can smell vitamin B1, thiamine, which smells very, very similar to decaborane. And you can check for yourselves that it does not in the least smell of chocolate. And that is why I showed you the vitamin B at the beginning of this episode. And this, to me, was like the smell equivalent of the Rosetta Stone. The Rosetta Stone is a classic in the decipherment of languages. It's a piece of stone that was found in Egypt, and it has the same text written in 3 languages, Demotic Greek, Coptic script, and hieroglyphic. And it enabled the decipherment of the hieroglyphs. And this was exactly the olfaction Rosetta Stone, because here was the smell of sulfur written 2 completely different ways, and the only thing those 2 ways had in common was their molecular vibration. So I think the best way to illustrate this, to make it really almost tangible or audible, is to translate the vibrations of these molecules into sound. So in order for the vibrations of frequencies of molecules to go down into the part of the spectrum that we can actually hear, I had to divide them by approximately 30 billion. That's 30 with 9 zeros after. So if you divide the vibrations frequencies by 30 billion, you translate them into the lower half of let's say, of the audible range. And let me first show you what it looks like with an alcohol, so methanol, and thiol or SH, or sulfide, the different names, same. So the sound of the alcohol, and now you will hear the sound of the SH compound. So they're quite different, quite different. Now let us repeat this computational experiment with, on the left, the sound of the SH compound, and on the right, the sound of the borane compound, the BH compound. And you can see that or you can hear that the two vibrations are very close indeed. And this is true for all boranes. All BH bonds are in that range of sulfur. So at the time, I was working at University College London, which is a big university and has a large and famous chemistry department. And of course, there were some people within the chemistry department who were familiar with boranes. So I was very excited. I contacted them. I was actually, on cloud nine about this. I was amazed. And I contacted them and I said, do you realize that boranes smell of sulfur? And they said, well, of course they do. What else is new? We've known this all our lives. They smell horrible and they smell pretty much just like sulfur. So I said, well, why didn't you tell me? And they said, well, quite rightly, they said, well, because you didn't ask. And so I was actually amazed. I went through the literature and, in fact, looked at the literature, the older literature, the first proper scientific literature on boranes, the Alfred Stock's work, for which he got the Nobel Prize. And it turned out that Alfred Stock had, on several occasions, described the smell of boranes in his papers, big, long papers in German. And one of them, I found an exact reference where it says, it smells very much like hydrogen sulfide. So this fact had been known since 1910 or something, and I didn't know about it. Although, to be fair, the vibrations of boranes were measured much later, in the 1940s. So even though the fact that they smelled of sulfur was known and should have been, how can I put it, should have been puzzle that people wanted to solve, chemists had mostly ignored it. And by the time the vibrations came along, well, nobody put two and two together. So this was pretty amazing. This was, for me, it was the moment where I decided that the vibrational theory was really worth thinking about.
So what happened after this momentous rediscovery of the smell and vibrations of boranes that everybody knew about, except me? Well, so I thought it would be interesting to try and replace the hydrogens on the decaborane with heavy hydrogen, with deuterium. And many people have asked me this over the years, but people say, why can't you do that with SH? So if you take SH, take a compound that contains an SH, and you replace the hydrogen on the sulfur with a deuterium, so it would be SD. What you get is you get pretty much identical size and shape, give or take 1 part in 10,000 or something, and the vibrations are changed by a large factor, by 0.7 to be exact. So an SH compound with a deuterium on the end should no longer smell of sulfur, according to vibrational theory. And that's all true, except for one small problem. And the problem is this: the deuterium or the hydrogen are not very firmly attached to the sulfur. And so typically they exchange one for the other. So if you put a compound containing an SD in water, which is full of H's, what happens is the deuterium gets exchanged for hydrogen within fractions of a millisecond, and therefore you end up with SH. So, for example, if I were to smell a compound that has a sulfur deuterium, an SD in it, it would immediately, when it hits the top and the nose, it finds mucus, all the bodily fluids are actually made up of deuterium water, just regular water, H2O, not D2O. And therefore it'll become SH immediately, and therefore the smell will go back to whatever it is normally. But this is not the case for boranes. Boranes do not exchange readily. So in principle, you could take decaborane and you could make a deuterated version of decaborane, and you could ask the question, what does it smell of? So much as I did before with citronellyl nitrile, it's easy enough to calculate pretty accurately the vibrations of decaborane and deuterated decaborane. So let me show them to you. If you look at the spectrum of decaborane and the different vibrations, you can easily identify those that are responsible, I believe, for the sulfuraceous odor. They're situated around 2550 to 2600. And there they are, and they involve a collective motion of all the hydrogens that are singly connected to a boron atom together, and that gives you a very strong peak roughly at the sulfur frequency. Now, if you compare what's happening there to what is happening in deuterated decaborane, what I've done is I have replaced each hydrogen atom in the calculation with the heavier atom of deuterium, that instead of a mass of 1, it has a mass of roughly 2. And now if you look at the spectrum, it's quite different. The vibrations of the BH bonds have been shifted down quite a bit. It's the largest isotope effect because you're doubling the mass of the hydrogen. And they're now outside the range of the sulfur vibration. So at the time, I had a Russian collaborator in the lab, and she inquired from some colleagues in Moscow whether the Institute of Inorganic Chemistry of the Academy of Sciences still had a borane research group, which they did, it turned out. So we contacted them, and we asked them whether they could make us a small quantity of decaborane with deuterium instead of hydrogen. And they said, yes, for $800, I believe, they would do such a thing. And so after a few months, they said the sample was ready. And of course, I had to go to Moscow to collect it. But before I did that, I wanted to know if they thought it smelled different, because after all, these people had been making boranes for a long time, and certainly they would know the smell of boranes, and therefore I wanted to know if they smelt their sample of deuterium borane, did it smell different? And so my colleague called them up at the institute in Moscow, and she said, what does it smell of? And they said, what do you mean? And she said, well, can you please go and smell the sample of deuterated decaborane that you've just made for us? And they were a bit reluctant, but they said, okay, we'll do it. Call us back in 5 minutes. So I think these must have been the 5 longest minutes of my life. I waited, then she dialed up the number again, and got through to the head of the lab. And he said, it smells different. How did you know? And so she said, never mind. That's good. We'll come and pick up the sample. So I went to Moscow and I picked up the sample. And it was actually not 100% pure. Unfortunately, there was a bit of hydrogen borane in it, but it smelled pretty different. Unfortunately, 2 things. I couldn't do the experiment where I tested it on naive subjects because decaborane is toxic, so I would never get the approval to have it tested on just a random collection of people to find out whether they agreed it smelled different. And the second one is that the sample got lost in one of my many moves, so I no longer have it with me. However, there is another way of doing the experiment, which is relatively easy to do, although not particularly safe. So don't try this at home. And that is, you can purchase from chemical suppliers a complex of borane, of BH3, the actual borane, with an amine, trimethylamine, And when you bring them together, there's electron exchange between the two, and the borane frequency is shifted down about 200 wave numbers from 2550 to about 2350. And if you do that, and you smell it, you gotta be careful. It is not nice stuff, but you can just smell it. It doesn't smell of sulfur at all. So that's another confirmation that the vibration, not some weird property of boranes, is responsible for the odor.